All right. Good morning, everyone, and welcome welcome in joining my session, The Art of VMware Performance. So, how can we optimize your clusters and workload for free? Yeah, we've got a quite nice turn up. I would say if you have any questions, keep them until the end of the session, because I do have almost 50 slides. So we're going to rush through them. Maybe important. All the slides are on my website, so you don't have to take a lot of pictures. You can just browse to the website, and they're all there. You can go through them. Every optimization is all mentioned, how you can do the commands and such. So, who am I? So my name is Jens Hermans. I'm from Belgium. I work for a partner there. I'm a senior VMware architect, as well as in the past, I did a lot of Horizon. Now it's a bit less, but I'm doing it anyway. Certified. I love photography, skiing, being in the mountains. I'm doing quite some social work, as in on the socials, and I'm heavily into the community. So I'm a vExpert, Omnissa Tech Insider. I'm part of the Belgian VMUG leadership team. So knowledge sharing and organizing community events is something that is near and dear to me. So what's on the agenda for today? Well, it's fairly obvious. We're going to optimize your clusters in the most efficient way. So we're going to talk about compute. We're going to talk about storage. I do have some bonus slides. Again, if we don't get to them, I highly recommend checking them out on my blog. So disclaimer. It's personal advice. It has been tested in the field. It has been implemented at a couple of customers of mine. It's running fine. We've seen major benefits, but of course, evaluate it at your environment, with your workloads, and don't implement it on a Friday evening, just when you go on a holiday. Test it, evaluate it. If it doesn't work, roll it back. I'm giving you the commands to check, evaluate, and implement. If it doesn't work, well, it doesn't work for a certain reason, of course. Second thing, if you're expecting to get the performance of a BMW, but you just bought like a Lada, it's not going to work. What we can do with this session, we'll tune that Lada to the best as possible. So don't expect that you're running a 4-node cluster with a 4-core bronze CPU to behave like a 32, 20-core, 20-node cluster. What we will do is we'll fine-tune certain specific compute settings that we really are going to get real benefits on it. I've got some examples that we get between 5 and 7% performance gains with just one tweak. So if we're talking about a vSphere cluster, a standard vSphere cluster, not a VCF, but it's also applicable for VCF, of course. We're talking about a cluster, X amount of hosts, running with 3-tier storage, vSAN, whatever, running a bunch of VMs. If we take a step back and we look at what does really a cluster, or what is a cluster made of, it's nodes. We're talking about physical boxes, Dell, HP, Lenovo, whatever, that are working together and handling individual virtual machines and their CPU instructions. So if we're going to take a look at the optimizations we can do on a hardware level, we're going to talk about BIOSes, firmwares, power, C-states, hyper-threading, NUMA. I think that those will be the main topics for today that we're going to talk about, also some vSAN and such. But if we're talking about Dell, HP, the first thing that I'm most frequently getting called into with support cases and what I'm seeing in the field, and that actually will be the biggest takeaway for today, is if I get involved or I do a log on onto a customer, I'll open up ILO, iDRAC, it's all looking fine, everything is healthy, and then I see something. The release date. It hasn't been patched since the initial deployment. That's one of the major things that I really want to take away is patch your damn systems, guys. It's 2025. If you're still running a HP server using an ILO version of 2020, there are security vulnerabilities, performance is left on the table, and especially stability issues, perhaps. If it's running fine since 2020, it's going to be stable, I guess, but just patch your systems. It will improve performance. It won't be a lot, but it's there. With that being said, let's start really fine-tuning our systems. So does anyone know, well, I guess you all know this overview. It's from the ESXi, but it's the same from vCenter. So you select the host, go to monitor, all the way at the bottom, overview, and you'll get the power settings. Is the top screenshot going to provide the best performance? Anyone want to pick a guess? Yes? No? Well, actually, no. Why? Because as you can see on the bottom slide or the bottom screenshots, on the technology side, it's saying P and C states. So what actually is happening, ESXi is now detecting at the on the bottom screenshot that the server or the hardware level itself is actually presenting P and C states towards the ESXi operating system. So the ESXi CPU scheduler is aware and can interact with the system itself, or the bare metal system and the bare metal CPUs itself. So talking about P's and C states, what are they actually? So it's fairly simple. A P and a C state is actually the state, or an active or an idle state, that an individual core of a CPU can be in. P stands for performance states. It goes from P0 till, most of the times it's P13, and it is actually the frequency the core is running. P1 is actually the base frequency. So if you're buying a CPU, I've got a home lab with the 4110. It has a base frequency of 2.1 gigahertz. That's my P1 state. P0 state is my turbo frequency. So most of the times you'll select a CPU based on turbo frequency and base frequency. And then you've got P3 till 13. Those are actually slower clock states. So if it's running on P13, it will be running at 0.1 gigahertz, for example. It's still active, but it's not doing a lot. C states are actually sleep states. So sleep states mean that a specific part of a core is getting shut down. For example, C1 is that the clock is getting stopped. C2 means that the phase loop, the phase locked loop is getting, so it's the frequency. So it's the chip that is actually maintaining the consistent frequency to schedule the CPU is also getting turned off. LLC caches are getting flushed. Every D or every C step with a higher number is putting certain parts of the core into in an off state, actually. So the deeper the sleep state, or the higher the C state, the less energy that individual core will consume. Why is it important? Well, it all depends on how we configure our BIOSes. So you should think, well, okay, as I said, if we put our host into max performance from a Dell perspective, we're going to get the best performance. Yeah, we're going to get the best performance, but there is a caveat. So talking about max performance BIOS settings, it's equivalent for HP, it's the same for HP, Dell, whatever vendor term they're utilizing. But max performance, what it actually means is it's going to enforce a P1 state, so the base frequency, on all our active cores, meaning it will never utilize that P0 state. So turbo frequencies are actually never utilized. So max performance means, from a BIOS standpoint, I'm keeping all my cores alive, but from a performance turbo frequency or a frequency standpoint, I would say, we're keeping the cores at a minimum. So we're leaving actually some additional performance on the table, because we want to make sure that all our cores are active. But is that important that all our cores are active? Well, yes and no, of course. It depends on what kind of workload, and that's why I'm saying in the beginning, test it with your workload that you're running. If you're running super mission-critical, sub-second transactional-based databases, for example, that might be the ideal setting. If you're running just a bunch of Windows, VDIs, you're leaving performance on the table. But how do we check it, actually? Well, fairly simple. Open SSH, type in xstop. I think most of you guys know it. Type in P for performance. So it's a performance overview of xstop. And then FF, I've hidden it, but it is for the average mean performance counter. It's just an average counter that will give you a value based on 100 that is telling you the individual CPU thread is running at base frequency, it's lower than base frequency, or it's higher than base frequency. So as you can see in this example, it was on my home lab. It's an a dual socket 8 nodes machine. All my cores were actually in a C1 state, so doesn't mean it's completely idle, but they're active. And if we look at the average mean perf, you'll see that this is actually, because my system was actually 100% idle, it wasn't doing anything. So I had enough wattage available that it was able to turbo boost. But normally, if you're running active machines and you have an active state, it should show 100% on all the cores. Which is great, yeah, but of course we want to have that percentage higher than 100%. And then if it's lower than 100%, it's idle or in sleep mode. So to change it and to allow ESXi to really utilize those CMP states, we actually need to change the maximum performance, or no, sorry, the BIOS configuration. As you can see, Lenovo is fairly simple because it showed it fairly well. It is showing that it's on purposely disabling P states, C states, and the C1 enhanced state if we're putting it in a max performance state. So how do we actually change it? All right, so how do we actually get to the point that ESXi is able to push those P0 states towards all those cores? Let me show you. It's my good friends. So as I said, I've got a 4110 at home. Base frequency and turbo frequency are, so base frequency 2.1, turbo frequency 3 gigahertz, P0 state and P1 state. But something really important if you're looking at the Intel AMD websites is that TDP value. And that is actually everything that is, you need to understand, so it is important to understand what is a P state, what is a C state, and how do they interact with each other, and how does it impact the frequencies and the performance it's able to be, to deliver. But it's all tied into that one TDP value. And TDP stands for thermal design power. Don't know why it's such a vague term, but it just means that that individual socket or that individual CPU is able to maximize or to consume 85 watts at a maximum. It can't go above that one because then it will just fry itself. But it means that those 85 watts in combination with a maximum performance, so all my cores are active, means that each individual core will get 10 watts. We don't have any additional, well, pretty much, and you know, I don't want to keep it simple. So there is no additional performance or wattage left to boost towards those turbo frequencies. So 100% performance is the max performance state. It means, yeah, again, it is base frequency with a minimal latency because we aren't swapping between P states and we aren't swapping between C states. So how do we actually let the system decide? Well, we need to change the BIOS that we can allow it to, well, utilize the active state, of course. That's the logical part because we want to have active cores. But in certain cases, if our system isn't utilizing its full potential, we actually wanted to allow certain cores to go into sleep mode because, as you're seeing, let me just get the pointer. As I said, the core clock in the C1 state is off. If we're talking about C3 state, the PLL is disabled, and the L1 and L2 caches are actually being flushed. So it's consuming less energy. The disadvantage, or the caveat, is, as you can see here, the wake-up time takes longer. So as I said, max performance, minimal latency. If we're introducing C states, we're introducing actually artificial latencies in changing those states. So knowing that, and if we are putting cores into sleep mode, does that mean that we got unlimited power? No, we're still capped to that 85 watts. But if we're putting certain cores into sleep mode, we're actually returning X amount of watt back to the, I'm going to say the resource pool, to keep it simple, to be utilized by other cores to go to the turbo state. And that's the thing, that a lot of people think, I'm buying a gold CPU, I don't know, it has a turbo frequency of 4.8 gigahertz, let's put it that way. Why isn't it running all the time at that gigahertz? Well, it's because that TDP value is continuously being utilized by other cores, and it needs to have that additional availability of wattage to actually go to the turbo state. So it's always short-term boosting for specific CPU instructions that are being asked by workloads. So if you've got a CPU or a system that is 100% utilized or 90% utilized, normally you won't never see cores being or going to the turbo state because it's always getting hammered. So that's why I'm saying you need to test it, evaluate it, because it is dependent on your environment and on your workloads, on your behavior, that you might get performance gains out of it. So how do we change it? Fairly simple. Lenovo again, or my home lab again, change it to efficiency favor performance, rebooted it, reloaded the system, and well, let's check ESXi top. Okay, I'm seeing C3 states, looking good. It's putting some cores into sleep mode, C1 states, and P states. That's C0, of course. So I've got cores that are in sleep mode, deeper sleep mode, and active cores. Great. So I just started up one virtual machine. You're seeing it at the top, one virtual machine, 4 vCPUs. I'm not running a lot. I just cleared everything. Just did a reinstall with ESX9 freshly. So I just spinned up a plain blank Windows virtual machine. But what I was able to see is, well, it's utilizing some cores. They're running at 100%. I was running some benchmark that I found. But if you check at the mean perf, or the average mean perf, I'm seeing that a core is now running at turbo frequency instead of 100%. So it is burst-based, but I am seeing more performance. If you're running a benchmark, I was running the Geekbench, and if you're testing, well, the max performance 100% versus this one, I was getting better performance in a global number, so I'm getting a higher number than before, which is great. My applications are running more efficient, they're running faster, because, well, single-threaded and multi-thread applications are getting better scheduled than before. So, we did it. Yes, well, actually no, because I did found something. So if you're running a Lenovo, for example, there is a caveat. The PNC states are actually being autonomously managed by the system. And because I was looking in ESXi and I only saw C states being propagated towards the ESXi, and no, I never saw P states. So I went into the documentation, looked at it, and it was, well, fairly obvious that apparently if you're running a Lenovo system and it's mentioning autonomous configuration, the hardware itself is still in control. So I had to put it in legacy modes to allow the PNC states to get really fully propagated towards ESXi. In my use case, why did it turbo? Well, because I was only running one virtual machine. If we're running 100 or 50 VMs, well, 9 out of 10, they all would have flattened at the base frequency. I really wanted to have ESXi in full control. And why do I want to have ESXi in full control of the system or of the PNC states? Well, it's fairly obvious. ESXi has been around for almost 25 years. They've been working with Intel and AMD systems since back then. They understand how virtual machines work. They understand how CPUs work. That ESXi CPU scheduler is super optimized. I think Joe mentioned it yesterday that, for example, AI workloads or database workloads are running near bare metal performance. It's because of that CPU scheduler being so optimized. So that's why I want to have ESXi in full control of my system that I bought. I just spent 20 grand on a system that I'm putting ESXi on. I want to have the full performance being presented towards ESXi. And it's just a fairly, well, easy change. I can test it, I can validate it. If it doesn't work out, roll it back. So I changed it to legacy, and now I got full control of the system. How do I check it? Fairly simple. Well, again, from vCenter, it's clicking on the host, monitor, scroll all the way down, overview, and then the power management. And now I'm seeing that in a balanced configuration, I'm having the full PNC state configuration. Maybe the most important thing to know, if it doesn't work out, you can leave your BIOS settings that way and just change the policy to high performance, and ESXi will enforce that base frequency for you. You don't have to reboot. You don't have to fiddle around with those BIOS settings. You're all good. So you've got full control from the ESXi, but you're still doing the same that the best practice from Dell or HP would have recommended. One thing I do want to note, if you're doing, for example, the Lenovo settings, had to custom or create a custom mode. If you're doing that and creating a custom mode, make sure to first put your host into a max performance setting, because it will also configure all the other settings, memory configurations, PCI settings, and such. If you're leaving it on a efficiency, then change it to custom, and then change only the PNC states. You're leaving all the memory controller, PCI controller configurations in an energy efficient state. You really want to have the max performance, and then change only the settings you want to change on your own. I've been talking for approximately 20 minutes. Why does it matter? Well, if you're looking at the AMD, so AMD, compared to Intel, has a lot of white papers on VDI, vSphere, vSAN performance. I think they're for the last 5 generations of, or 4 generations of AMD CPUs, but it's fairly comprehensive. It's easy to read, and especially it shows you what are the real in-world benefits of changing those settings. So as you can see, small block random reads, which is most of the times the typical workload you're seeing, or that I'm seeing, I would say. If we're comparing high performance no C states versus balanced with C states, we've got 7% performance loss. So talking about a 20 node cluster, we're talking about 1 or 2 physical nodes of performance that we're just losing because of 2 settings. So that's the biggest takeaway, I would say. Figure it out, implement it on a test cluster, validate it, push it to production if it's all fine. And if you're running VCF, validate it with VCF ops, and then you're even better to go. So that was power states. What about hyperthreading? Fairly simple. It's there for a reason. Utilize it. It's not 2 for 1. It's 1.5 for 1. If you don't, well, that's from an architect standpoint. Don't calculate your sizings with hyperthreading. Always utilize personally, or always utilize the physical cores only. But if you're only, well, to be honest, I haven't seen any vendors, but I know there are some vendors that enforce you to disable hyperthreading. But leave it on. It is there for performance gains. Just wanted to mention it. So, and then we've got the next one, NUMA. Frank is here as well. He's the god of NUMA, I would say, Frank Denneman. So NUMA is, let me ask you another question. Are you aware of the max config of Broadcom or VMware? So it's just it's a web page that shows you all the maximum configuration states you can implement on a specific product. So for ESXi, I didn't include 9 actually, but so for ESXi 8, you could actually create a virtual machine with 768 vCPUs assigned to that one. I have no idea what for system you need to have to run that, but you can. If you want to try, well, don't do it on a Friday evening just before you go on holiday and on the production cluster, but you could try. I won't be. You can't call me if you want to have if you're having issues, but you need to be aware that if you're configuring such large monster VMs, that NUMA is actually a thing. So what is NUMA? Well, NUMA is actually a logical construct of a CPU that will indicate how or what the bounds are of an individual CPU. So for Intel, because they're utilizing monolithic design, it is just if you're using, like with my home lab, I'm using dual socket 8 cores, so my NUMA domains are 2 NUMA domains with 8 cores each. And why is it actually important? Well, it's fairly simple. If I'm creating a virtual machine with 10 virtual vCPUs, how is it going to be divided, or how are my CPU instructions going to be handled? Yeah, the ESXi doesn't really know, do I have to split it up? Do I schedule them instantly or them on both times? And most of the times, they'll schedule the CPU instructions on both CPUs at the same time. And that will increase, well, latency, wait times, and what does that mean? Slower performance, sluggishness, and such. Why is that happening? Well, we're actually scheduling CPU instructions on both CPUs Because they're interconnected with a UPI, it's QPI. This is still showing QPI, but it's actually now UPI, so Unified Path Interconnect. It's just actually the highway between the two CPU sockets. But it's handling everything. PCI, PCI communication, memory communication, inter-CPU communication. It's handling everything. But it's a highway between two cities, so let's put it that way. There is latency. So what you actually should do is, if you're running a 10 vCPU VM, it's logical, I know, but I've seen people that aren't aware of that, and I've seen a lot of people, I've seen a lot of software vendors that come at a customer, they implement a virtual machine, are completely unaware of NUMA, they implement, I don't know, for example, a 10 vCPU VM, and the application is running super slow, and and you as an IT administrator, yeah, you didn't see it, and it's running for the last 2 years at a horrible pace. So it's fairly simple to validate. If you're running, if you're running a VM that is larger than a NUMA, please be aware there is a caveat or a performance loss. So how do you solve it? Well, fairly simple. Upgrade to version 8, bump your hardware version of that virtual machine to a version higher than 20. And there will be an option now, it's under the advanced VM settings, that the CPU topology can be automatically assigned based on what ESXi is actually seeing on the NUMA side. So that's maybe one of the reasons why you should actually upgrade your hardware versions of your virtual machines. vSphere is actually real, or ESXi is also, or VMware, well, let's put it that way, is really implementing additional features that you might have never heard of, to really they understand how the system works, so they'll try to optimize and give you the best optimal configuration for your virtual machine. If you're still running a hardware level 4, yeah, you're going to run into these issues. So let's say I'm running still 7, what do I need to do? Yeah, I'll manually need to change my configuration to 2 sockets, 5 CPUs, for example. How do I check it in the wild? Or in your environment, fairly simple. Download RV tools. I've taken an example from a customer. I've obscured it a bit just to make sure that they don't know who they are. But so they were running a 10-node production cluster. What did I do? I validated what is the smallest CPU size available. Well, it's a homogeneous cluster, so they were all running dual sockets, 16-core CPUs, and then I just validated what is my largest VM, and bam, we got one. It was a Cisco ICE machine, you know them, and it was over-provisioned, and it had real-world impact in terms of performance. We bumped it down to 16, and it was running between 10 and 12% more efficient, just based on that individual change. Why is it? Well, it all has to do with ready times. It is congestion, actually. I'm talking about that highway, but it's also the highway from the virtual machine towards the CPU itself. And you can check that as well. Xtop is, to be honest, the perfect tool to evaluate performance. If we're talking about storage performance, CPU performance, you can evaluate everything. So, example here, this is also a real-world example of a customer of mine. I've secured it all also. We've got virtual machine 1, 2 vCPUs. It has a ready time percentage of 73. Does anyone think that's good, bad? Indeed, that's horrible. So what you actually should do is we're running 2 vCPUs, so we should divide that 73 by 2. So we've got a CPU ready times of 35%. If we're talking about ready times, well, 0 to 5% ready times, we've got that BMW. We're running at bare metal performance. The system is actually being underutilized. 5 to 10, yeah, that LADA, we've tuned our system, we did our sizing right. We can say to the business, yeah, we did our sizing perfect. TCO-wise, REO-wise, we're good, we're bang on the buck. We can maybe squeeze in a bit more, but then we need to expand the cluster. 10 to 20, we're getting a bit cramped, guys. Maybe you should look at offloading the cluster a bit or adding an additional host. Higher than 20, yeah, that BMW is really on fire. We're getting real impact on the OS level. Applications are running slow. End users will complain, or business users will complain. Everything. If you're then losing a server or doing some maintenance, yeah, you're gonna have a bad time. So make sure to really validate what are your current ready times in your environment, and then, well, act accordingly. Validate within RV tools if you're running or if you're over the NUMA domains for certain virtual machines. It doesn't only apply for CPUs. It's also applicable for memory because, as you know, 2 sockets. They've each got their 4 individual DIMM channels or memory channels. Yeah. Example again. We've got 16 single DIMMs in our 4-channel dual socket machine. Yeah, so it means that our NUMA domain has 46 gigs max local memory. If I'm provisioning a virtual machine with 72 gigs, I'm doing inter-cluster or inter-socket memory allocations. What does that mean? Latency, performance decrease, and such. So please be aware of that as well. SubNUMA. Now we're going to get deep. So this is only applicable for AMD. Why? Well, it's not. But so with scalable Xeon 6, Intel has moved away from the monolithic and went into a chiplet design. But SubNUMA for Xeon 6 is still. I haven't tested it. I haven't validated it. So you can implement it. Plus, just be aware that you need to evaluate it and test it and see if it's beneficial for your environment. But for AMD, it's been there for quite a while. There are, again, white papers on it, if you should use it or you shouldn't use it. Why? Because AMD uses a multi-chip or a chiplet design, and they use CCDs, which is a core complex, which individual CCXs are cores. And the advantage is you can configure a SubNUMA configuration based on how you are going to divide those CCDs in your system. So if we're talking about MPS, so it is mentioned, or you can configure it in the BIOS using an MPS value: MPS 0, MPS 1, MPS 2, MPS 4. MPS 0, what does it mean? Well, we'll just make one massive NUMA node with the latency included. Why is that maybe interesting to utilize? If you're running that monster virtual machine, now you're averaging out actually the memory latency across the entire system. So there is a reason to utilize MPS 0, but it's super vague, it's super specific, and for VMware-based workloads, it isn't recommended at all. So why even? MPS 1, that's just out of the box how it's configured. If you're just rack and stacking it, plug in the power, press play, install ESXi, your system, or AMD system will be running in MPS 1. One individual socket is one NUMA domain. MPS 2, 2 CCDs are actually a NUMA domain, so we've got 2 NUMA domains per physical socket. MPS 4, we've got 4. So why should we use it? Well, so again, from the AMD performance white papers, MPS 1 and 2, they are, mostly preferred for just generic workloads, MPS 1 especially, because that's the default. MPS 2, again, there are no real performance gains, only if you're running fairly specific workloads. But that MPS 4 one is actually, there is a reason why you should could implement that one, and that is, as I said, I'm an EUC guy. Yeah, if you're running VDI on AMD, MPS 4 has some real performance gains. Why? We're actually creating 4 NUMA domains that the ESXi scheduler can utilize and parallelize individual workloads and schedule them individually. If we're running MPS 1, our scheduler is always trying to figure out one massive block and trying to figure out the individual workloads into that block. Well, you know VDIs, how much vCPUs do they got? Between 2 and 8, I would say. If we're talking about VDI, most of the times 4 vCPUs. Yeah, as you can see, if we're running a 32 core AMD divided by 4, we're running a CCD or a NUMA node complex of 8 cores. That 4 vCPUs perfectly fit. So if we split it up in 4, we've got actually 4 individual, we were parallelizing our scheduling capacity and performance of that system. What do we see in terms of performance? It's, again, depending on the workload and how hard the system is getting hammered, between 5 and 10% performance gains out of the box. Again, you need to test it with real world, but I've seen some major benefits with that one. So conclusion, upgrade to 8 or 9 to utilize the dynamic NUMA allocation. It's called CPU topology, actually. Right-size your virtual machines, fairly simple. Again, every optimization that I'm talking about, it's 10 minutes work, maybe a reboot, and you can evaluate it fairly quickly using Xtop. Prefer hyperthreading equals 1. What does that mean? It is actually, it means that it will include hyperthreads within the NUMA configuration. And that is especially important to know that it has a performance impact utilizing small core systems with large memory footprint. So most of the times, the impact that it has is on databases. That's where I'm seeing smaller hosts with like low core counts because of the licensing, but with high amounts of memory. If you're enabling prefer hyperthreaded equals 1, it will include the hyperthreads, and it can have some impact, but it can also have some performance gains. If you're really trying to optimize databases, there is a white paper on that one. Frank Denneman did a massive deep dive on that one. Just read his blog. His blog was really insightful, I would say so. And then, yeah, sub-NUMA configuration. If you're running AMD, look into it, especially if you're running VDIs, or if you're running, your workloads are running under 16 or 8 cores because of the CCD cores, the CCD complexes that can possibly fit in that sub-NUMA. As I mentioned, Frank already wrote some books on it. He's got a blog on it. It's fairly, it's really interesting to read. Don't read it on a Friday night because you'll fall asleep right away. So that was compute. What about vSAN? I do have some 3-tier optimizations, but it's fairly complex because we're going to talk about queuing. It's in the additional bonus slides, but again, they're all on my blog. So what about vSAN? So anyone running vSAN? I guess a lot of you guys. Anyone running OSA? All right. So I don't know if you're aware, but OSA back in the days had a limitation that their cache disk was 800 gigs. Nowadays, with vSphere 8, they've bumped that cache disk capacity limit to 1.6 terabytes. So depending if your physical drive is large enough, and that most of the times is the issue that I'm seeing, if you're having a cache disk that is 1.6 gigabytes, you just need to change one setting to really utilize that 1.6 terabytes. And it's the enable large write buffer command. So enable it, reboot it, recreate a disk group, and you'll get some massive benefits on it. Small block size reads, writes are really up to 100. There's also, again, the KB, it's mentioning between 100 and 200% performance gains. Because it's actually just doubling the amount of this write capacity that it's available within that individual disk group. So if you're running multi DGs within a host, you're really pushing that additional performance for that group. Again, it might be even beneficiary to upgrade that individual cache disk to a 1.6 terabyte drive. Again, SQL optimizations or SQL. That was my Flemish coming through. There is also, again, a white paper on that one. If you're running SQL on vSAN, make sure to implement the trace flag 1800 command, or the 1800, yeah, I'm going to say, I think it's the command, within the SQL properties. Again, major performance gains. Why? Actually, SQL is or SQL is now actually utilizing the 4 megabyte block size, which is the native vSAN block size. So it's aligned. So vSAN is able to utilize or to provide better performance to the SQL. So conclusion, it's been quite a lot. I hope it was interesting. But so what are the key takeaways? Well, I think a lot of performance is left on the table when you're just picking up your server out of the box, racking and stacking it, and powering it on, and don't do any tweaks on the BIOS. Just go through the manuals. There are best practices on HP and Dell. But as I said, they always recommend using max performance BIOS settings. Implement the PNC states, and you'll really see some major performance gains. Right-size your virtual machines. It's a best practice. It's common knowledge, I know, but I just want to mention that I'm seeing there are always 1 or 2 virtual machines in your cluster running over the NUMA nodes, and it's most of the times wrongdoing, but it has a real performance impact. Don't use any specialties. Most of the times, the base configuration is always the best one, except for BIOS and right sizing. But what I'm talking about that one, this one is actually more to do with the 3-tier configuration. So modifying queue depths, changing LUN depths and such. It does have an impact. It can be there can be performance gains, but most of the times what I'm seeing is it has more impact on the performance than real gains. And then just as I said, update your systems. Super simple, stability, security, performance-wise, it doesn't hurt to just patch your. Well, yeah, it doesn't hurt. It hurts because you need to work on a Friday or in the weekend because you need to patch those systems. But there is a reason why software vendors and hardware vendors bring out new firmware versions. With that being said, thank you so much. I really appreciate that you fill in the survey. I've done this session in Frankfurt and in Belgium. There was positive feedback, but hearing your feedback is always, so I can tune and tweak the slides even more. So thank you so much. If there are any questions, feel free or to ask them. As I mentioned, slides are available on my blog, PDF and embedded PDF. And we've got 2 minutes, so I'll keep the bonus slides hidden. So you've got an incentive to visit my blog, so I've got more visits. All right, thank you so much.